Welcome to another lecture in fundamental mechanics. Today we'll begin to learn about the physical laws and principle behind rotational motions. Let's begin with the rigid body model. What is a rigid body model? It is simply, as the word rigid suggests, it's an object that we will treat that it doesn't change its size or shape during a motion. The purpose of using this model is that we can treat the rotating objects as a single entity that does not change its size or shape during the motion, so that we can simply uniformly treat that object as a single entity for simplified calculations. Number two, let's review briefly about the rotational kinematics. We learned from our previous lectures about angular velocity. Angular velocity is defined as change in theta in time. And angular acceleration, alpha, is change of omega, the angular velocity, over time. It is not to be confused with the linear acceleration or tangential acceleration. And let me write here the relationship, actually, if you want to make that equal to one another. The tangential acceleration A is equal to radius times the angular acceleration. In the same way, velocity, linear velocity, is equal to radius times angular velocity. So just remember, to go from rotational to linear, you have the radius component multiplied to it. Now, knowing this, we can rewrite the kinematic equations. In the linear form, we have the final velocity is equal to initial velocity plus acceleration times time. This, in a rotational form, is the final angular velocity is equal to initial angular velocity plus angular acceleration times time. And consequently, you have the in general, the final position is initial position plus the initial velocity times time plus 1/2 a t squared. That is exactly the same in rotational form. You have, instead of the position, you have the theta. The final theta is equal to initial theta plus omega initial t plus 1/2 alpha t squared. And finally, the third equation, where you have v squared is equal to initial v plus 2ad. Here, the only difference is that instead of the displacement, we have change in theta. The total change, the theta final minus theta initial, the total change takes a place for the displacement in the linear version. So now we have here a rewritten version of the kinematic equations. And of course, these equations assume you have a constant angular acceleration. And by using these equations, you can solve the kinematic problems in the same way that you did with the linear versions. Regarding the signs of rotations, we covered before that the counterclockwise rotation, this way, is positive, and the clockwise rotation, this way, is negative. This is a convention, and the reason, where does this come from? Why is counterclockwise is considered positive? It comes from the right-hand rule, a concept that we haven't yet encountered directly, but it's used many times, applied many times in science. Right-hand rule. And that is, you take your right hand and you simply curl towards your palm. And now with your right hand, the direction of your curl is counterclockwise. And that's why the counterclockwise rotation, which is the direction of the curl, is a positive. And the opposite direction, clockwise, is negative from your right hand perspective. One more preview is that the angular velocity is a vector. It has its direction. But contrary to your intuition that it should be towards the direction of the circular motion, the actual vector direction of the angular velocity is the direction of your thumb. So in this case, it's pointing towards this way, and in that way, it's pointing towards the opposite direction. Your thumb points at the same direction as the angular velocity vector. This concept will come later on in this chapter. We're talking about the angular momentum. Now let's talk about number 3, center of mass concept. Let's consider any rotating object. We encounter many objects that are rotating in everyday life. Consider a wind turbine that is rotating at a certain angular velocity, or even a pizza dough. A chef is rotating a pizza dough is stretching into a bigger pizzas. Now, as you see the rotation of these objects, about what point does it rotate? So, for example, think about the pizza dough. Is there a point that the chef will put his finger on that the entire dough is rotating about? And the answer is yes. Remember that for every rotation, there exists a point where everything else will rotate about that point. For example, consider the 3 uniform shapes that you see on the right-hand side here. You have the circle, you have the equilateral triangle, and squares. Now, if I ask you, as these objects begin to rotate counterclockwise, in a positive direction that is, where would be this point of rotation that the entire object is rotating about? And if your intuitions probably tell you here, right at the center for each of this object. And you're absolutely correct. Your intuition tells you that in a uniform object like these, the point of rotation would be right in the middle. But why should it be in the middle? How can we explain this physically? Well, consider in a circle, a uniform circle, the center is where the distances to every point on the circumference of the circle will become equal. So logically, that should be the point in the center that becomes a point of rotation for this object. And a similar argument can be given for triangles and squares, because that's the average point of all points of the objects inside. But let's go a little bit further to solidify this. However, think about these 2 scenarios. What if the shape is now non-uniform? So for example, from an equilateral triangle, now the triangle is reformed as a bilateral triangle. And now if you spin that triangle around, as in this figure on the right hand side, will it still rotate about its relatively center position? Or will it change? Will it shift to a different position? And if then by how much? Or consider now a circle, the uniform circle as above. The shape remains the same, but this time the bottom half of the circle for some reason is heavier than the top half. And now consider like a pizza dough. And if you now rotate this pizza dough, will it rotate about its center point? And your intuition will tell you no. It will shift it somehow down towards the heavier side. So we have to ask this question. What determines this point of rotation? And this point of rotation is called the center of mass. And as the word describes it, it represents the center point of its mass distribution in a given object. It takes account the shape of the object in terms of distances, and also the mass distribution in terms of mass. The definition of center of mass is it is a motionless point where every particle in a rigid body rotates about. In other words, when you put your finger on the center of mass of a rotating object, that point will not move. There will be no rotation happening at the center of mass point. Now, how can we find the center of mass in a given object? Let's consider a very simple case of two equal mass that is connected by a massless rod. So this rod does not play any role in this rotation. You have M1 and M2, and they're going to spin like this. Where will be this center of mass, where you can put your finger, and that's where the entire object rotates about? Your intuition probably will tell you again, it will happen right here in the middle. Now let's walk through the mental process, the intuition that your brain has done of finding this out. So let's say that you're saying that from this midpoint, we have equidistance here, x1 and x2. And what your brain has just done is that my center of mass is, I take the mass distribution of the first mass and the distance from an arbitrary point plus the second mass, and you do the same. You add them up and divide it by the sum of the two objects. And let's see if this comes out the same as your first answer. So let's consider the mass, both mass M and 2 is 2 kilogram. And let's say the rod, the entire length is 4 meters. Down half, you will have 2 meters and 2 meters on both sides. So at this, you will tell from this point on, let's call this is my 0, and here is 4 meters. I'm saying that my center of mass here is 2 meters. That's what my intuition told me, without doing any mathematical practice. But let's just see if this equation confirms what my intuition has, or your intuition has done. So here, the first mass one is 2 kilogram, and from this point here, on this axis, the distance to that is 0. And the second object is also 2 kilogram, and from that reference point, it is 4 meters apart. And then you divided this by the sum of the two masses here, and that is equal to 2 meters from the center. So this is a useful formula. Now let's expand that. That was for two objects. And now you can also imagine if you have many more objects, say another mass here, another bigger mass here, or even you can have in two-dimensional case many masses around. No matter how many particles there are present, this principle, you can just scale it up and have a general expression, which you can see over here. This is a definition, the mathematical description of finding calculating the center of mass. And it's divided into two x and y coordinates in 2 dimensions, but the expressions are exactly the same. For instance, you will just simply replace where you put x lengths in the x-axis with the numbers in the y-axis. That's the only difference. So this will give you a coordinate, the center of mass as a coordinate, x-coordinate and y-coordinate, and that will be a center of mass in a given object. Let's take a look at a little bit more detail. It is 1 over the total mass, that is the denominator here. You just simply adding up all the masses, m1 till mn. And that is simply you put it out of the sigma at 1 over m. On the numerator, you have mixi, and this indices I goes from I to the number of objects being involved. So m1, x1 goes together, added m2, x2, m3, x3, plus dot dot dot, mn, xn, the n number of the number of objects. And then you divide it by the sum of the entire mass. And that will give you the x-coordinate of the center of mass and y-coordinate for the center of mass. Let's solidify that concept with example 12.1. In this example, the center of mass of a barbell. A barbell consists of a 500-gram ball and a 2-kilogram ball connected by a massless 50-centimeter long rod. And we're asked to find the center of mass in this situation. So take a look at this representation here. This case, now in the above case, if the two balls have equal mass, your intuition as well as our calculation confirm that the center of mass should occur somewhere in the middle, right at the middle. However, in this case, you have a heavier object on the left. Now, what does your intuition tell you this time? The center of mass should be shifted towards left. I know that empirically, but by how much? How much is the mass related to the distance it shifts from the center middle? And that's when the equation of center of mass comes in very handy. So let me write down here again. The center of mass for x is 1 over m sigma mi xi I. In this case, you have only two objects, so let's just put it in together. The total mass is 2 kilograms plus 500 grams, so that will be 2.5. And then in the summation, you will have m1 x1 plus m2 x2. Now, where would you put your origin? The practical thing is, you can choose where you put your zero marks to be. And I'm going to set the zero marks at the end of this barbell, at the same position of one of the objects. Why? Because you'll be multiplying 0 for its distance and you'll be eliminating one of the objects. It just makes the mass that much simpler. So have the x0 at the one end of the an object. So this will become 1 over 2.5. Here you have 2 kilogram times 0 plus m2 is 0.5. And the distance from this point all the way to the end is 50 centimeters. So that is 0.5 here. So that would be, this is 0. You have 1 over 2.5 multiplied by 0.5, 0.25 here, and that gives you 0.1 meter. Aha, so the center of mass occurs 10 centimeters. Remember where you set your 0. From the 0, it is 10 centimeters away from it. So here, this length here is 10 centimeters. And from the center of mass to the other end would be then 40 centimeters. Now, part B. It is asking, what is the speed of each ball if they rotate about the center of mass at 40 RPM? Okay, so we have to first equate this angular velocity in terms of speed. And that we know that the speed in linear velocity is radius times angular velocity. Now notice these two balls will have different radius r1 and r2 from the center of mass. So they will have a different linear speed because they have different radius. So for velocity 1, you will have r1 share the same angular velocity, and velocity 2 is equal to r2 omega. Omega is shared because everything on the, think about a record player or a CD player, or any dust particle that is rotating. It doesn't matter how far it is from the center of the disk. They all will rotate in terms of angle, the same angle together. However, your linear speed is related to how far you are away from that center because you're covering a greater circumference. So angular velocity is shared, but the linear speed is proportional to how far it is away from the center of rotation. So in this case, for velocity 1, you have r1, which is 0.1 meter. Angular velocity, that's what we need to solve here. Now, let's see here, angular velocity. Angular velocity, we're given 40 RPM, but that is not in SI units, so we need to convert that into a radians per second. Now that is equal to 40 revolutions per minute. We know per revolution, there are 2 pi radians per revolution. And then, of course, there's there is 60 seconds in a minute. Now this is per minute, so the minute goes in the bottom. You have 1 minute here and 60 seconds on the bottom. And we have there about 4.19 radians per second. Now we know the radians, the angular velocity, omega. We can simply substitute that here to find the answer. That would be here 0.1, 4.19 for velocity 1. And here we have 0.4 times 4.19. And that will give us the speed 1 and 2 respectively. So just reiterate this problem in your own time. You can pause the video and make sure you know how to go from linear concept or from rotational concept back to the linear and back and forth. Make sure you feel comfortable how to do that. And here, make sure that you understand the steps how we found the center of mass. Now let's continue with our discussion. We have learned about how to calculate center of mass in a given object. Now we're going to further generalize our result to any arbitrary shape. Up there we considered circle, triangles, and the squares, but these concepts really apply to any kind of given arbitrary shape. But there is one catch to it. So consider this arbitrary shape that I provide here. Any shape. Now, as I told you, you can choose your own origin anywhere you want to get the distance. Now, this shape is made out of many particles. And each of the particle, if this shape does not have the equal distribution of mass, all will have different mass density depending on where the object is, and also its distance, its vector position, right? Its coordinates will be all different for every single particle here. Now your job to find the center of mass of this arbitrary shape is to add them all up individually and divide it by its total mass. Now the latter part is easy, but the first part is not easy at all. You quickly realize that adding individual particles discretely, I underline here, discretely, that is what we're doing with the summation here, it will become an impossible task for any practical object that is not uniform. If it's uniform, there's a shortcut that you can take, but discretely, there's no way you'll be able to count up every single particles, even in a rounded object. So what we need to do, we need to generalize. We have to develop a little bit more powerful tool, going from discrete to continuum. And you guessed it, I've used these tricks before. We will go from summations to integral. Now to do that, we have to do some substitutions here. So this is the form that we start with. And we need to understand how this term makes sense. So now consider an arbitrary shape, which is represented on the right-hand side over here. This part here. Now, what I'm going to do, as I've done with other concepts with the integrals, I'm going to chop this large objects into many individual unit cells. Unit cell meaning that each of the cell here and cell there is all have equal dimension. And now you can chop this objects as fine as you can conceptually in your mind. And you will realize that as your unit cell becomes smaller and smaller, the uneven mass distribution, the distribution becomes small, it becomes less diverse, that you will get to a point where the unit cell is small enough, you can dissect any surface area that contains the same amount of mass per given area. So this now, for example, is your cell, unit cell. And in this cell, and if you have your neighboring cells all with equal dimensions, each of them will contain a certain amount of mass delta M. And as you chop them off to smaller and smaller pieces, these individual delta M will become relatively, and in roughly estimating, becomes equal. You can in fact dice it up so small to get to a point that delta M of all these unit cells become equal. And so what you can do then is that you can set mass to be an equal unit cell. So each of the summation will have the same delta M. So this becomes a constant out of the summation. So that's the key here. So now you have only X, its position in terms of the summation, multiplied each of those summation, xi times delta M, x2 times delta M. Each of them is multiplied by the same constant delta M. Now, once you have that expression, then we will take the limit of delta M going to 0 of xm, and that is taking the limit of this entire expression. And that will become 1 over m. The summation will become an integral dm. And that is now a more generic definition of center of mass. This works for any general, any arbitrary shape. So you are going to integrate the position x with respect to the mass. Now that is something that we haven't done in the past. And why are we doing this? Why are we taking an integral with respect to mass, not for dx and dy? And that is to say that there is a neat mathematical trick that you will learn and that you will see shortly. And this is there's a whole sections dedicated in a calculus class to deal with these issues. So there's a neat mathematical technique of doing a surface integrals, and that is what we're going to utilize in this in the physics concept. So take a look at the example 12.2. And hopefully this concept will be solidified with this concept here. Now, what we're going to do here is now we have not just one or two objects. We have here gazillions of particles inside of this rod. And we are to find the center of mass in this particular shape. Now, you have a uniform rod, meaning the mass is equally distributed throughout this rod. Now, if I ask you, giving you this uniform rod of length L, where will be the center of mass? What does your intuition will say? At the half point, right? It will happen probably at the half point. Yes. Now, let's see if we can arrive to that conclusion using the a powerful integral tool that we have just learned. So, let me write here that the original equation is 1 over m integral of x dm. Now, as strange as it may sound, that my job every time of using this equation is to substitute dm to dx so we can actually integrate it. So this substitution, the relationship between dm and dx, will depend upon the shape of an object and how the mass is distributed in terms of lengths. We are to find out the relationship between its length or its physical dimension to how the mass will be distributed. Now, in this case, this is a uniform rod. So think about it. The longer the rod portion that you have, the greater the mass it will have. And as you increase the amount of length, the more mass that it will have. So for example, I know that having a certain length of this rod correlates to a certain mass of that rod, a portion of that mass. Now, if I take the entire length of the rod, meaning the entire rod, then the small m becomes the total mass of the rod. Now then the question is, how does dx, an infinitesimally small amount of length, relates to dm? We know it is related. How can I make this equal? A simple trick is using the ratio. The ratio of my lengths, dx divided by the total length L, is equal to dm divided by total mass of the rod. Now, if you need to, pause this video and think about this concept to see if it sinks into your mind. The longer the rod portion I have in terms of lengths, the more mass proportional that I will have. And if I have the entire length of the rod, which means the entire rod, the mass of that entire rod is the total weight, m. So my dx, the infinitesimally small amount of increment of change of length, is equal to, in terms of ratio, dx divided by the total length is equal to infinitesimally small amount of mass divided by the total mass. So now I have the relationship between dx and dm. So as I told you before, your job is to substitute dm in terms of dx so that you can actually integrate in a meaningful way. If you try to integrate it like this, in respect to m, it will give you a trivial result. You can try it and it will give you a very trivial result. All right, so let's see here. dx over L is equal to dm divided by m. Now this relationship is specific to this situation above. Depending on what kind of shape you're dealing with, you will have a different relationship of dx and dm, and that is the key point. That is the exercise that you have to figure it out. Now in this case, you have dxl dm divided by m is equal, so dm is equal to m divided by L times dx. So let's do the substitution. Then here I have 1 over m, x, and in terms of dm, I'm going to put m divided by L dx. Now, both m and L are constants. So m will cancel out here, and then you have 1 over L outside of the integral, x dx. And now this becomes a definite integral because you're integrating from 0 to the total length L. And that is 1 over L. The integral of x dx is x squared over 2 going from 0 to L. And that is 1 over L, L squared over 2. You put 0, that is 0, so it doesn't count. 1 of the L cancels out, and voila, you have L over 2 is the center of mass. Now, again, that is a trivial solution because you already knew it. However, this still serves as an important segue for understanding this concept, because once you go off from a uniform an object, then you run into a trouble. Your intuition can no longer tell you exactly the value. That's why we're practicing using this powerful tool. Now let's finish off part B. Part B, we're asked about the tangential acceleration. All right, so again, the tangential acceleration A is related to the angular acceleration by radius. And since the radius we're given is half of the total length, the total length is 1.6, we have 0.8, and you multiply alpha, which is 6 radians per second squared that is given, and that's simply you can find the acceleration. Now we started about the rotational motion, and we will continue with this concept in our next lecture, and we'll apply this principle that we learned today to solve more complicated problems and more interesting problems. So thank you so much for your attention. I'll see you next time.